Hey everybody, welcome to today's video. You remember in an earlier lesson we talked about lattice enthalpy, which refers to the energy that has to go in to overcome forces of attraction between ions in an ionic compound. Today we're going to talk about something analogous to that. When we're dealing with covalent bonds, then we talk about bond enthalpy, the energy associated with breaking 1 mole of a particular covalent bond in a mole of compound. So if I had a mole of this compound and I wanted to break the carbon to bromine bonds in a mole of those, I would essentially get these two pieces, and the energy that has to go in, again, to break a bond or overcome forces of attraction here, would be 276. Notice again, it is an endothermic process. Now, in the same way that we had tables of lattice enthalpies, we also have tables of bond enthalpies. So we're going to be using this table. It's in your textbook on 316. But before we get mathy with that, let's just go to the particle level for a minute and consider the reaction between nitrogen gas and hydrogen gas to make ammonia gas. So I want us to visualize what's happening on a particle level. Here's an N2 molecule, and we need not 1 hydrogen, but 3 hydrogen molecules. There's one, here's a second, and here's a third. So in order for this reaction to happen, energy has to go in to break the bonds. Can you see all that? Okay, so anytime we are breaking bonds, and again, you know, when we say breaking bonds, you have this image of snapping or breaking something physical. There's no physical thing that is the bond. The bond is just the Coulombic attraction, and I have to put energy in to overcome that force of attraction and pull the atoms apart. So I put energy in to do that, and now I'm going to put energy in to overcome that attraction, break the bond, and I'm going to put energy in again to break this bond, and then lastly, the third hydrogen. Energy goes in each time to break those bonds. Now, I want to make ammonia molecules. And whenever particles are allowed to attract to each other, energy is released. Okay, so I want you to listen carefully. There's a little bit of a time lag between the sound and the picture on my video here, but I'm going to construct ammonia molecules by allowing these particles to attract. And the energy is released. As particles attract, energy is released. As these particles attract, energy is released. So there's one NH3 molecule, and we'll keep going. Exothermic process with energy released as you form new bonds. Energy is released. So we have two things going on here. We have energy going in to break bonds, and then we have energy released when we make the new bonds. This is the relationship. The enthalpy change for this reaction is going to be calculated by collectively considering all the different energies that had to go in to break the bonds. That collective sum is a positive amount, and we're going to add up collectively all the energies that were released as we made the new bonds. That collective sum has a negative value. And then when you add these two pieces together, you're going to get the enthalpy change for that particular reaction. So now let's do the math that's involved. Let's start again with breaking our nitrogen bond. Okay, so this was our nitrogen molecule. And I go to my table of bond enthalpies. Zoom in. And you can see at the top, the N to N bond has a value of 163. But wait, before we get going too fast, is that focused? Do you see down here, I have another nitrogen to nitrogen bond that's stronger? And that's because it's a double bond. And then also I have a nitrogen to nitrogen triple bond. So before we can use this relationship to calculate the enthalpy change, we have to have Lewis diagrams. So the very first step in this process is to look at your balanced equation and draw the Lewis structure for each of your reactants and products. So remember what we did in our Lewis structure video. We start by adding up all the valence electrons. Nitrogens have 5. There's 2 of them. So my target number here is 10. I draw my atoms together with a single bond that used 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I recognize that my second nitrogen doesn't have an octet. So I'm going to change that non-bonding pair to a shared pair. Still don't have an octet here, so I'm going to do it again. And that proves to me that my nitrogen molecule has a triple bond. Okay, hydrogen molecules are easy. Hydrogens have 1 valence electron. There are 2 of them. So my target number here is 2. Now this 3 I'm ignoring for the moment. I'm drawing my hydrogen molecule, the single bond there used up the 2 valence electrons. Now I recognize that I have 3 of those. So draw it again and draw it again. Okay, those are my reactants. On the product side, I am making ammonia molecules. Nitrogens have 5 valence electrons, hydrogens have 1, but there's 3 of them. 8 is my target number. Nitrogen bonded to 3 hydrogens, used up 2, 4, 6. 8 is my target. I'm going to put 7, 8 right there. That's the Lewis structure for ammonia. Now I have 2 of them, so I'm just going to draw that picture again. Now that I have my Lewis structures in front of me, I can use my table of bond enthalpies. So, the first bond that I need to break, let's get this all on the page here. I need to break the N triple bond N bond. That bond has an enthalpy value of 941. That would be kilojoules per mole. And then the hydrogen to hydrogen bond is 436, but there are 1, 2, 3 of those that have to be broken. So I'm writing 3 times 436. Okay, now I'm going to grab my calculator and add up that total, 2,249. That is the total amount of energy that is going to need to go in to break all the bonds. I'm just going to remind myself that's a positive value. Now I move over to the product side. These are the new bonds that are going to form. And I can see that I have to form the N to H bond 1, 2, 3, 4, 5, 6 times. So the N to H bond which has a bond enthalpy of 391, is going to form 6 times. Now, very important here, that value is negative because remember, when bonds are formed, energy is released. Every time I form the N2H bond, 391 kilojoules is given off. That's an exothermic process with a negative value. So 6 times negative 391 is negative 2,346. Okay, so energy going in was this much, energy being released was that much, and the value of delta H is the sum of those two numbers. When I add positive 2,249 and negative 2,346, the enthalpy change for the reaction is negative 97. Now don't forget to put the unit for your enthalpy change, that's kilojoules per mole, and this is an overall exothermic process. Let's do one more for practice. So we have the reaction N2H4 plus 2 F2s to yield N2 plus 4 HF. My first step is to draw the Lewis structures. N2H4 is going to be 2 times 5 plus 4 times 1, a total of 14. Now, you might just start stringing your atoms together like that. I want to remind you from our Lewis structure lesson, hydrogens are unique in that they only form one bond. They never have non-bonding pairs. They never have two bonds. So you can never string hydrogens together like that. Instead, nitrogen is going to bond to nitrogen, and the hydrogens have to be peripheral on the outside. So as I used these bonds to connect the atoms, I used 2, 4, 6, 8, 10. My target number was 14. So there's 11, 12, 13, 14. Okay, fluorines. Fluorines have 7 valence electrons. There are 2 of them. Target number is 14. So I put the 2 fluorines together with a bond. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. This 2 tells me that there are 2 of those molecules in the reaction. Draw them both. 2 fluorines and 1 N2H4 molecule. Coming over here to the product side, N2, if you recall, we did that one earlier. Nitrogens bond together with a triple bond. And then my hydrogen fluoride. Like hydrogens have 1 valence electron, fluorines have 7. That's a total of 8 for my target number. H bonded to F, that's 1, 2, 3, 4, 5, 6, 7, 8. Notice that I never put lone pairs on hydrogen. Hydrogen gets 1 bond, that's it. Now this 4 tells me that there are 4 of these molecules. So I'm going to draw all 4 of them. All right, those are my Lewis structures. Those are going to help me find the correct bond enthalpies on my table on page 316. Okay, remember, the equation tells us that the enthalpy change is equal to the energy needed to break bonds. So for that sum, I'm going to be looking at my reactants and breaking all the bonds. That value is always endothermic. And then I'm going to come over here on the product side and add up the energy that is released every time I make a new bond. Those values are all negative because that process is exothermic. All right, so let's come over here. First, I see that I have the nitrogen to hydrogen bond. And I see that there's 1, 2, 3, 4 of those that have to be broken. Nitrogen to hydrogen, 391. And there are 4 of them. This is energy going in. I also have to break the nitrogen to nitrogen single bond. And that has a value of 163. Just one of those. And then I have the fluorine to fluorine single bond, and there are 2 of them in these 2 molecules. That is 155. The fluorine to fluorine bond, 155, and I have 1 in each of the 2 molecules. So I add up that total, and the total value is positive 2,037. That's the total amount of energy needed to break every one of these bonds in the reactants. Moving over to the product side, my first product is nitrogen to nitrogen triple bond. And there's only 1 of them being formed. That bond is 941. And remember, because I am forming a bond, I want to put a negative value. That bond enthalpy is released as that bond forms. Next, I've got the hydrogen to fluorine single bond. There are 4 of them, 1 in each of the 4 molecules, and that bond enthalpy is 567. And remember, because that bond is forming, that energy is being released, negative value. Excuse me, when I add up all of those values, I get negative 3,209. Okay, the delta H value for this reaction is simply the net sum, this magnitude and sign added to this magnitude and sign. Now, before I add those pieces together, can you see that it is the product bonds that are stronger in this particular reaction? The magnitude of the new bonds we formed is larger than the magnitude of the bonds we had to break. And also, it takes more energy to break the bonds, or is more energy released in making the products? Answer, for this particular reaction, more energy is released. So when I add these 2 pieces together, the net sum for my enthalpy change of reaction is negative 1,172. Don't forget the unit, kilojoules per mole. Now, I want to do one more thing. You remember that we've had a different way of solving enthalpy of reaction when we did our thermochemistry unit. At that time, we learned about solving for enthalpy change of reaction using heats of formations from the index in the back of your book. Remember, we had thermodynamic quantities that gave us heats of formations. And the equation that we used was to take the heat of formation of the products and subtract the heat of formations of the reactants. So very quickly, I want to remind you, in this reaction, our products are nitrogen gas and hydrogen fluoride. And our reactants are N2H4 and fluorine. I should be putting the coefficients here. 4 of these. We had nitrogen and 4 HFs. For the reactants, we have N2H4 hydrazine and 2 fluorines. Okay, so if we're using this method for calculating enthalpy of reaction, we're going to add up the heats of formations of our products, starting with nitrogen. And remember that elements in their elemental forms have heat of formation of 0. So we're going to start with 0. And then we're going to add to that the heats of formations for HF. HF has a heat of formation of negative 268.61, negative 268.61, but we have to multiply that by 4. So we're going to get that total sum. And then we'll be subtracting the sum of the heats of formations of our reactants, starting with N2H4, heat of formation positive 9540. And the 2 F2 molecules. Now, fluorine, F2, is an element. Elements have a heat of formation of 0. So this would be 2 times 0. Now you grab your calculator and you add the sum of our products. And that sum is negative 1074.44. Subtract from that the sum of heats of formations of our reactants, 95.40, and that gives us a delta H, negative 1074.44 minus 95.40. That gives us negative 1169.84 kilojoules per mole. Now let's compare. When we did our bond enthalpy method, we got this answer. And with our heat of formation, we get this answer. They're not exactly the same, but they're really darn close. Which of those is considered the true value? And the answer is, using heat of formation is considered to be the true value. Here's why. When we do our delta H using bond enthalpies, the table that we're using is a table of average bond enthalpies. Turns out that this strength of the N to H bond of 391 can differ slightly from molecule to molecule depending on what else is going on in the molecule. So these values are good averages to give us an estimate. So when you visualize the molecules that you are breaking bonds and then reforming new bonds, that method gives you a good estimate of delta H. But when we use heat of formation data, that's considered to be more the true value. Okay, I need to talk about one more thing. This is a goof that I made in the earlier video called Formal Charges and Resonance. When we were at the end of the video at 17 minutes 50 seconds, I was looking at resonance for nitrate molecules. Do you remember this? And we drew 3 different possible Lewis structures for the nitrate polyatomic ion, and we ended up realizing that formal charges didn't give us a right answer. And we said resonance is where the true structure is actually a blend. And furthermore, we talked about this double bond being delocalized, not here, not here, not here, but sort of smeared over the whole structure. And it was like nitrate actually had 3 equivalent 1 1/3 bonds. Well, it turns out that single bonds are longer than double bonds. Double bonds are longer than triples. A 1 1/3 bond would be somewhere between a single and a double, actually a little bit shorter than a single. And in this video that I made, I mistakenly said that the 1 1/3 bond was a little bit longer than a single. So my bad, that was a goof, but I just needed to correct that for you. And again, that was a lot today, but I hope that you feel comfortable drawing Lewis structures for a balanced equation and using bond enthalpy values to get a good estimate of delta H, remembering that any bonds that you break require that energy goes in, and any new bonds that you form are going to release energy. Okay, guys, thanks a lot.